It's a pleasure to be here, and a disclaimer at first. So I am not a turbulence expert by any stretch of the imagination. I'm a knuckle-dragging astronomer. But what I've tried to do is, and I model diffuse gas around galaxies. But what I've tried to do is read some papers from your communities and apply it to our systems. And if you think what we're doing is fundamentally wrong or misguided, please come and talk to me so we can learn. Anyway, so let's go. So if you were here for Drummond Fielding's talk on Monday, he gave a beautiful introduction to this field, and he has really gorgeous high-resolution simulations, much lower resolution simulations. But the fundamental takeaway from that talk is that there's multi-phase gas everywhere in astrophysics, and this comes fundamentally from atomic physics. It stems from the way that atomic radiative cooling works in diffuse plasmas. And so the canonical system I'll talk about is something where there's a hot phase with a temperature of about 1,000,000 Kelvin, and there's a cooler phase with a temperature of about 10,000 Kelvin, right? So there's overdensities of about 100, sometimes 1,000 if the hotter phase is a bit hotter. And so this has been seen in observations, many observations. This field entered a renaissance when there was a new spectrometer on the Hubble Space Telescope, and they saw lots of 10 to the 4K gas sitting in the halos of galaxies, and in great abundance, very high mass fraction. And this is fundamentally weird. Okay, so this is stuff that is overdense by a factor of 100, just sitting in the atmospheres of galaxies, and that's roughly, overdensity of 1,000 is about the overdensity of a rock in the sky. Okay, that's not a stable situation, right? So you've got to throw it up or let it fall down. A lot of times we think what the galaxy is doing is juggling. It's just doing this galactic fountain kind of thing. And the trouble is that if you throw it up, then you can just do very simple estimates, and there's an acceleration time, which is essentially the time scale it takes for a cold cloud to sweep up its mass, right? And then you can compare that to a destruction time, which this community calls a cloud crushing time, but is essentially a Kelvin-Helmholtz timescale, mixing driven by shear, which is shorter than that, right? So just from this consideration, it seems like you should never be able to accelerate something by blowing on it, right? If you have a galactic wind that tries to lift your cold cloud up, then shear instability should mix it into the background. So, so what's going on? So if you run hydrosims, you'll find that this happens. Okay, so if you run hydrosims, it looks like the cloud is just mixed into its surroundings and destroyed. And if you track the mass, it looks like the mass is just going down, right? But in fact, okay, let me play that movie over.
What was the temperature of this cloud again?
So the hot gas is about 1,000,000 Kelvin, and the white stuff is about 10,000 Kelvin, which is the stable phase in galactic halos. Okay, and so the key ingredient which enables entrainment and survival of the colder phase is radiative cooling, right? So it's just atomic transitions which cool the gas. And what happens is if you mix the gas, and that mixed gas can cool on a time scale shorter than the Kelvin-Helmholtz time, then it can transfer its mass and momentum to the cloud and enable the cloud to grow. So, we've been thinking about it fundamentally the wrong way. We've been thinking, all right, we have a sailboat, we blow on it and try to accelerate it. Instead, what you should think is that the hot gas crashes into the cold gas, right? And then it mixes, and that mixed gas can cool very effectively because, sorry?
That's my Siri, I'm sorry.
Okay. Well, Siri knew the answer way before. The cool gas the mixed gas can cool, and it's basically like, a train wreck or a car crash. You all pile into one another, and just by momentum conservation, if enough cars crash into one another, they all start moving at some new speed, right? And so this requirement that the cooling time be shorter than the mixing time gives you a critical size for the kind of cloud that can survive. And this has been verified by many simulation groups now, right, in hydrosims. So here's a picture, where you're below this critical scale and you get destroyed. If you're above the critical scale, then you grow and survive, and you grow this very long cometary tail. And you can see that now the velocity difference with your wind is very small, and you've grown considerably in mass. And you can figure out these two things just from momentum conservation. It's like a simple freshman physics problem. Okay. So how does this work in detail? And that's where you guys come in, right? So the basic unit of what's going on is a radiative turbulent mixing layer, where gas of different densities and temperatures are mixing, right? There's a Kelvin-Helmholtz instability that's driving mixing and turbulence, and then the mixed gas is cooling. And so there's mass transfer from this hot phase to the cold phase. And as someone remarked on Monday, this is very much like the problem of turbulent combustion, right? You have a temperature-dependent reaction, and you have some fuels that's turning into ashes. And that's exactly what we thought. So we started trying to read papers about turbulent combustion and apply it to this problem to try and understand it. So there were two key questions that we wanted to understand. The first is scaling relations, right? So order of magnitude, what is the enthalpy flux of the hot gas? And it's mixing in with the cold gas at this certain velocity, which is of order the sound speed of the cold gas multiplied by this odd ratio. So this is a cooling time over a sound crossing time of the cold gas. For this community, really the relevant thing is if I take this as a turbulent velocity, and we've measured it in our simulations, then this is something like what you guys call a Damkomler number, I believe, to the 1/4 power. And at least for us, I think maybe for you, this is like, well, of course. For us, we were like, what? Why 1/4, right? We would think of, there's some sort of turbulent diffusion of heat, and you would expect a square root power. So this was the first thing that we didn't really understand. And then the second thing was that you can run simulations at varying resolution. And as Drummond showed on Monday, the interface is fractal, meaning that the interface is scale-free, and the area will increase as you increase your resolution, just like the length of the coastline increases as you look at smaller and smaller scales. But and then you would think, well, if you have more area, you will have more mixing and more cooling. But the thing is, if you run very low resolution simulations and you run higher simulations, they have the same mass growth rate. They have the same surface brightnesses, even though the morphology looks quite different. So that was disturbing to us. So these were two questions that motivated us. So right, so this is an illustration of the fractal structure that Drummond talked about on Monday. Right, you can see the area grows as a power law with resolution, as you expect for a fractal. Okay, so this is the converged mass growth I mentioned, right? So if you change simulation resolution, the area changes with resolution, going larger and larger with increasing resolution. But the mass growth rates seem pretty converged and independent of resolution. And the other odd thing was that we had previously run simulations of individual mixing layers, and then we found a scaling with cooling. But then this was the more expected scaling that you expect for a diffusive process, right, where square roots are involved. So that was interesting to us. So we started reading papers on turbulent combustion, and basically we decided that the resolution problem was kind of the obvious one, right? It's very similar to if you stir a cup of coffee and you're trying to mix some cream in it. Well, you're not very sensitive to small scale structure. You're right. Your mixing time is basically your outer eddy turnover time, and you're not sensitive to the exact value of molecular viscosity. That just tells you where the cascade terminates. So we ran a bunch of simulations, which I don't have time to go into, to verify this. And in particular, it was an article of faith in this community that you need to resolve something called the field length, where heat diffusion balances cooling to have converged results. And that's true for morphology, but it's not true for mass growth rates or momentum transfer rates. And then the other interesting finding was that both the simulations I had mentioned were right. That if you characterize the strength of cooling by this Damkolmla number, right, the ratio of the eddy turnover time at the outer scale to the cooling time, then you have a strong cooling regime and a weak cooling regime. And in the strong cooling regime, you have something that looks like essentially more single phase turbulence, where everything comes to a sort of a sort of mean thermodynamic temperature, right? It looks like standard diffusion, and you get the square root scaling. Now, if you're on the strong cooling phase, what happens is that even within the mixing layer, the gas is multi-phase, right? So here you see within a mixing layer, there's hot gas, there's cold gas, and what changes through the mixing layer is the fraction of the relative fraction of those things. And in those, then you get this 1/4 square root scaling that I mentioned.
So what you mean by multi-phase means that you have more of a gas that was initially hot or initially cold, right?
That's right. So you have two gas with very high temperature and density contrasts.
It's not a thermodynamic term.
Well, they have different thermodynamic temperatures. Yeah.
But don't think in thermodynamics you have solids, you have liquids, you have gas.
That's right. Correct. Yes, they're all gases. Yes, thank you. Thank you. Yeah, sorry. You know, you get trapped in your own world of jargon, and yes, yeah. Okay, great. Okay, so I'd be interested, this is how we explained it. I'd be interested to know, but you probably have much better models for this. For this 1/4 scaling. So we thought, well, if you're mixing and cooling at the same time, you're not cooling at just the rate of a uniform medium, right? Because you have to mix before you can cool. It's the mixed stuff that's cooling. And we're used to similar situations in astrophysics where you have a combination of elastic and inelastic collisions. Say you're doing a random walk, right? A photon is doing a random walk. If you have a combination of, if you have a medium which is both scatters and also absorbs, then the probability of absorption is typically the square root, well, the geometric mean of the probabilities of just pure scattering and pure absorption, right? It's sort of essentially a random walk with some probability for absorption. And there's also the same case for the random walk of a thermal electron where you can hit an atom and undergo cooling, right? So we said this is the same for a turbulent eddy. Then you can make predictions for what the cooling rate should be for a piece of plasma. And then you can test whether the scaling works. It's not just the cooling rate, it's not just the eddy turnover rate, it's the geometric mean of the two. And indeed, in the simulations, in the mixing layer, you can see that you reproduce these scalings, right? So if you now use this as your effective cooling rate, rather than what you would expect, as the straight cooling rate for a uniform medium, then you can understand this square root quarter scaling. So essentially, because now you have this new cooling rate, and you get your diffusion coefficient is turbulent diffusion coefficient still this, and so you get this 1/4 square root scaling. So I would note that this has been seen in turbulent combustion data, right? This 1/4 power law. The only real paper I could find trying to explain it was this sort of relatively early paper. If there are better ways to explain it, please let me know. Because this 1/4 power law turns out to be quite important to us. But okay, and then you can build analytic mixing length models. Maybe that's not so interesting. But one thing that's important to emphasize is that people try to constrain, the nature of the phase, the temperature jump at interfaces between hot and cold gas. And then they say they have all these different models: cooling flow, shock heating, conductive interfaces, turbulent mixing, which is this one. And then, run simulations and then essentially predict line ratios of atomic lines, which depends on the temperature PDF, right? So basically what they're probing is the temperature PDF, and they compare observations against these simulations and say, oh, this model is good, this model is bad. These predictions, at least for this turbulent mixing, have nothing to do with the physics of the mixing. As you all know well, when you have a mixing layer, there's always a laminar front attached to the interface where you have microscopic heat diffusion, right? And it's that's setting the thermodynamic temperature distribution. And so you can run simulation. So it's basically the difference between a coarse grain quantity and a fine grain quantity, right? So the sort of fraction, the relative amount of cold and hot gas in a two-phase medium is a coarse grain quantity. But at the interface, there's truly intermediate temperature gas that's set by microscopic heat diffusion. And that's a fine grain quantity. And that only depends on thermal heat, the microscopic heat diffusion, which is conduction. And so you can run simulations to verify that, where you change properties of the turbulence, you change properties of the cooling, and what really matters is the heat conduction law, and you can alter that. And you can show that you can write a simple 1D model that will reproduce the temperature PDF. So we were quite happy with that. How much longer do I have? Okay. Okay, so on Monday, somebody asked, what about magnetic fields, right? And so if you put magnetic fields at an interface like this, it will get amplified by vorticity, right? So turbulent dynamo. It will also get amplified by cooling, just through flux freezing. And so then you'll end up with strong magnetic tension. And that strong magnetic tension will suppress the Kelvin-Helmholtz instability, and the interface will end up looking pretty laminar, right? So this beta here is something that we use to denote the initial ratio of gas to magnetic pressure. So high beta is weak magnetic fields. So you can see even when the magnetic fields have an energy density that's very small initially, it grows until it just suppresses mixing at the interface. But now, if you do this not in a shearing layer simulation, but where you have a cloud and you blow gas on it, then it's very strange. Mixing is very efficient, and the cloud grows and entrains at a rate that's very similar to purely hydrodynamic simulations. And this is something that we don't quite understand yet. If you all have ideas, would love to hear them. One thing that we've been pursuing is that we think that, so here's a movie, and so the top is just temperature, and the bottom is emission. Essentially, you can see the cloud develops streaming flows, counter-streaming flows in the tail, right? Which we believe are actually related to the Darius-Landau instability that was talked about earlier in this conference. We're still trying to understand that, but it's still a miracle to us why this system, which looks so different from the cometary tails in the hydro system, should still have the same mass growth rate. Okay, and there's a young student here right there, finishing his first paper in grad school, and I thought this would be a great point to advertise it. So what about molecules and dust? So 10,000 Kelvin is the temperature floor if you're photoionized, right? If you become self-shielding to photoionizing radiation, which happens if your cloud is larger than a certain size, you can cool to lower temperatures, and that's seen in the observations, right? You see plenty of molecules and dust flowing out of galaxies at high velocity. You know, how can we understand it? That stuff, right, is at 10 Kelvin, 100 Kelvin. That implies it's overdense by, you know, factors of 10 to the 4, 10 to the 5. That ought to be impossible to entrain. That's like, you know, really a brick. And he ran simulations. So before, people had always capped the cooling at 10 to the 4, and he let it go down to low temperatures, and he found that actually it entrains pretty well, like very easily. So this is the Mach number of the cloud, right? And it approaches the Mach number of the wind, meaning that it entrains. And more interestingly, the effective overdensity of the cloud is not 10 to the 4 or 10 to the 5, but it's, you know, it's like that of an atomic cloud. It's about 100. And then, so what happens is that when the cloud has the wind blowing on it, it's mostly atomic. And then it's only after it's co-moving the wind that molecular gas starts to cool out. And you can understand this quite easily just from this ratio of the mixing time to the cooling time that I mentioned earlier, but simply within the cloud, right? So within the cloud, when it's being entrained, there's very strong shear. And so if you try to form molecular gas within the cloud, it will get mixed in and be destroyed. But after you're entrained, when the shear dies down, then this ratio of the mixing time to the cooling time becomes much larger, and you're able to form low temperature gas. So it's basically, you've got this bubble wrap that's keeping you at low overdensity, and if you try to form some dense gas, it gets destroyed, and only after the shear dies down and turbulence dies down, you can form it. Okay, and the very last thing I'd like to talk about is driven turbulence. So I've told you about a laminar flow, essentially a wind sweeping over a cloud. What if you just drive turbulence throughout the medium, which is something that will happen a lot in realistic astrophysical systems. So this was a simulation done by Max Gronke, and so you can see here, you get what is known, the technical term for this is a mess, right? So I think the main thing I want to impress on you is that you start to get a power law distribution of masses. And so mass is broadly distributed across a range of scales. It's roughly scale free. And the very interesting thing is that this power law has a very special index, right? It is, you know, the cumulative distribution has a -1 power law, which is known as Zipf's law, right? Which occurs over and over again in many, many different systems, right? So the distribution of energies in cosmic rays, the distribution of dust masses, so in dust size is a different power law. But if we translate to masses, it is the distribution of initial masses of stars, where gravitational accretion is thought to be important. It also appears, and in fact, it appears in tons of sort of physics systems, right? In human sociological systems. The frequency of words, I think this is where Zipf's law was first discovered, right? Of a certain length, has this power law, city sizes, YouTube subscribers, you know, income, all these different things. And I've tried to look at the literature of all these different fields, and everybody has their own favorite explanation. And it's a really interesting problem. So I've been thinking, you know, even like the distribution of sizes of bubbles in the ocean has this distribution. I've tried to think quite long about this, you know, and you know, we've come up with some sort of story. I'm not fully convinced of its truth, so I'm not going to try and, you know, inflict it upon you. I've also been thinking about analogies to the turbulent cascade, but I guess basically I would like to say, well, here's an interesting problem. You know, if you guys have good ideas about this, would love to hear them. This particular way of looking at it is taken from people who are trying to explain the sizes of cities, and they're trying to use the fact that things tend to grow, and we see this in our simulations in this fashion, right? Essentially, this is exponential, And if it's random, it gives rise to geometric Brownian motion. And you can show that under certain conditions, this will give rise to a power law distribution. We've run Monte Carlo sim to see this, but not yet, still thinking about this. So I think I'm up, and here are my conclusions.
Thank you very much. Excellent talk. Let's give him a round of applause. Questions?
Yes.
So if you have 1,000,000 degrees, 1,000 degrees, the 1,000,000 degrees is going to be fully ionized gas, and the 1,000 degrees are going to be
10,000
weakly.
usually.
Pardon?
10,000.
10,000. But you said.
So it's photoionized.
But you also had the hot stuff was hotter than that, wasn't it? You had two temperatures.
Yeah, the hot stuff was 1,000,000, and
that's
then
what I meant. So the hot
stuff
stuff is fully ionized.
Yeah.
And the cold stuff is weakly ionized.
In canonical scenarios, it's also fully ionized. It's
not
ionized
a 10,000. Not a 10,000. It won't be.
No, it's ionized by radiation that has a lot of energetic photons above a Rydberg, and so they just knock off the electrons. And only if the cloud is big enough, then that shields you from this ionizing radiation, and then yes, indeed, you can cool to much lower temperatures, which is what he was looking at.
Well, at any rate, it seems to me you'd be in a plasma physics regime, not in a hydrodynamics regime, so you'd get all sorts of plasma waves and stuff going on that are missing in hydrodynamics, so I don't think a hydrodynamic description is going to capture everything.
Well, okay, so there's a few things in there. Certainly, I think MHD is the correct picture, not just pure hydro, right? Which is why we're trying to understand what magnetic fields do. But in terms of whether hydrodynamics is applicable, I mean, typically the mean free paths of, ions in the system are still much smaller than the sizes of the system. Yeah, and in particular, once you have magnetic fields, the gyro radii are much, much, much smaller than any other scale in the system. Yes. So, we think in these systems, hydrodynamics is fine. There are hotter systems like galaxy clusters where you cannot ignore kinetic effects. So the plasma instabilities become important, fire hose, mirror, all of that. But at these lower temperatures, we don't think that's true.
Fire hose is an MHD instability.
Well, it depends on, a pressure anisotropy and, okay, anyway, yes.
So you had two contradictory statements. I agree with the second one, but I wanted to point out the first one. You said lately that conduction was very important, and I agree with that.
Right.
So when you described your coffee cup with the mixing of the milk, you said, well, there are no transport or diffusional processes that are important. I like to point out that this is not the case. What you're doing, you're stirring the coffee. So by stirring and stirring and stirring, you're giving more time to diffusion to catch up with the characteristic time of the flow. So diffusion is actually important on doing the mixing, which is your equivalent of conduction. Exactly.
No, so maybe I completely agree. So finally, microscopic diffusion is what's mixing the things, right? And the stirring is, is increasing the surface area, all of that, and so the diffusion. Right. But what I'm saying is that you can change the diffusion coefficient, right? And that's not going to change the mixing time. What sets the mixing time is the outer scale mixing time.
Well, there is no point to change the diffusion coefficient because it is characterized by temperature, by pressure, by whatever substance you have there. But you can change the characteristic time of the stirring.
That's right. I agree with that. Okay. I agree with that. My point was just in numerical simulations, a lot of the times the diffusion is numerical, so it's just going to change when you change resolution.
Those are not good simulations. Okay. You should stay away from those.
One more question.
Thanks for the talk. In the cases where you didn't really have turbulence on the batch, this was your kind of lowest resolution plot that you showed at the beginning, and kind of also the MHD, where the turbulence had been suppressed by the field lines.
Yeah?
Yeah. So, are you saying that the rate of the cooling is the same even in those? Because one couldn't really appeal to the sort of independence of the mixing rate because of
I think all
turbulence
you
in such
care about
cases.
is that two of them, so even if you have, basically like very little inertial range, right? As long as, you're mixing things on the outer scale at roughly the same velocity, then you're going to get the same answer. So they're going to be mixed at some rate, and then they'll just end up in the same simulation grid cell, and then be mixed artificially. But as long as you resolve that outer scale fairly well, say by 10 cells.
Is there a regime before the transition to turbulence, which it looks like that left-hand plot is in, and which it also kind of looked like your MHD plots were in, because they didn't have the turbulence, where the mixing rate is
so
the same?
there's also, something that I haven't talked about, which is that even when once you are entrained, right, and there's no turbulence driven by shear, you get acoustic pulsations, right, which develop due to pressure fluctuations from cooling that essentially mix fluid at the same rate. I guess all I'm saying is that basically if you're mixing things at macroscopic scales at a certain rate, then you will end up with converged results. Yeah.
Thanks.
Let's ask if there are any questions from our virtual audience. If not, let's thank Peng for a wonderful talk.